about a minute. And I've started the recording and take it from there. Okay, so welcome to CET236 circuit analysis. My name is Kershaw, and I assume you're all in the right room because I don't think there's any other classes, I don't know, even in this building today. There might be some downstairs, I'm not sure. So let's have a look. I'll get my scrolling finger working. So that is what we have for the semester, right? We want to learn about resistive circuits. We want to learn about circuits with resistors, inductors, and capacitors. So that here there are several of these little boxes, and you should be able to see, maybe, and go there, and go there, and you should be able to see that each box has a label with the value of the resistor, or the values of the resistors that should be in there, okay? So, don't necessarily believe that the resistors in there are the right value. So one thing you're going to have to get used to is trying to read the values, right? I'll talk about that a little later. You should all know about resistors, right? Ohm's law, V equals R. You've probably done some physics, even if it was a while ago, and that's where we start in this course. The trouble is we want to make it a little bit more useful, a bit more complicated. And to do that, we need to apply several, I'll call them algorithms. There's a thing called mesh analysis, another thing called nodal analysis. There's a thing called superposition. And there are Thevenin and Norton's theorems. We're going to do all of those things, first of all, for just resistive circuits, and then we're going to go back and do them again when we add capacitors and inductors. Right, so these guys are resistors. They're usually about that size, at least the ones we use. They have 4 color bands. The color bands tell you what the value is. This is a new lab. In the old lab we had a big poster with the color bands up there. I might see if I can figure out where that poster got. Let me just write that there. I usually end up at the end of the lecture with a whole series of to-dos just to remind me what I need to do. So that's their resistors. The other 2 components that we're going to deal with are called inductors. here we go. There might be in the battery, which I think capacitors. So, or capacitors. Right, that thing there is a capacitor. Anybody heard of a capacitor before? Oh, I've got some people. Okay, so that's alright. So, the things you're going to get used to doing, hopefully, this is not going to draw for me. There we go. The things you're going to get used to doing, maybe, to draw resistors, right, inductors, and even though that looks sort of similar, it's curly, whereas the resistor is straight zigzags, and capacitors, right? So if you ever see Rlc circuits, that's what it's talking about, resistors, inductors. We're only starting, we're not going to touch inductors and capacitors for a while yet. The reason they're drawn like that, resistors, funnily enough, try and stop current flowing through as much as the current wants to. Right, so it's like putting a zigzag in the way of the current. Inductors are just coils of wire, copper wire usually. So if you just want the current to flow through from a battery, for example, it will. It's just goes straight through. The inductor has zero effect. What has effect is because of those coils of wire, if the current changes, then you get interactions between the EM waves, the electromagnetic waves, travelling down the inductor. So it's only when things change. Capacitor is drawn like that because that's the way it's built. It's two plates separated by some sort of an electrolyte usually. So these things here, they're basically two plates and they're separated. These are called ceramic capacitors, so they're separated by a ceramic. The difference between analysing resistive-only circuits and analysing circuits with all three of these in it is the resistive circuits, we just use real numbers all the time. E equals I. When we move to the other two, then we need to use complex numbers. And I'm going to probably use the wrong term for most people. Most people use, or mathematicians tend to use the symbol I for the unit complex number. I'm not going to, because electrical engineers use J. The reason electrical engineers use J instead of I is because we electrical engineers use I to represent current. U equals I. Only. And to stop things getting confused, we use J. Okay, bit of a tangent. So all of these notes are available in OneNote, and you may have received an invitation to join the OneNote. If not, I will make sure there's a link to the OneNote notebook up on Blackboard so you can access it. I used to draw everything on the whiteboard and then take pictures and post those. This way I can just draw directly and make it available, and I don't have to take pictures afterwards. So there's a list of all the topics. The nice thing about being back in the lab is we get to use all these things. Right? There's 4 pieces of equipment, but you don't have to learn how to use it. Anybody got any idea what that is? Okay. That is a capacitor. Okay. How about that one? Well, if you can read it, it says digital multimeter. So it's got some data into that. This one here is a function generator. And this is a new one. But it's a really funky one. So we're not going to use anywhere near the functionality that is going to generate sine. And this is an oscilloscope where we can connect the codes up to the circuit and see how the voltages change. So one of the nice things, and I know there aren't that many nice things, about having to teach this course remote was that I started to use LT-SPOS. And the nice thing about LT-SPOS is you can simulate the circuits we're going to use in the lab before constructing and try and get some sort of an idea of what to expect in the lab. So you'll see all the labs now have an LT-SPOS component as well as actually building the circuit. Now, I don't know whether I'm going to get you to do the lab today. The reason is I've only got 12 benches. I don't know whether we have all the equipment. I don't know whether we can plug in. If you take, I meant to check that. I don't think some of this is here. Yeah. So we'll see. I might just get you to do the ELT stuff. What I do want to do starting next week is do the labs, and I'll have 12 people in here and 12 people in the lab next door. And you can do the labs individually. Okay, I don't want to get people to work too closely. No. Okay. Still going through this? Oh, there we go. I came in and got some pictures of the equipment earlier. So there's our power supply, there's our oscilloscope, there's our function generator, and there's our multimeter. Okay. So what I would like now is, this is me, my name's Peter Fitzsimmons. I have degrees in electrical engineering, masters and bachelors, and I have a degree in PhD in control systems engineering. That's my email address. I'm just an adjunct here, so I don't have an office. If you need to talk to me outside of class or before and after class, use that booking link and that'll get time on my calendar. Currently, I have virtual office hours and Tuesdays, I think it's set up to be. But if that doesn't work for you, let me know, and we can sort out. As far as what to call me, I prefer Peter. If that's not a runner, Professor is okay. I answer to just about anything. Hey you. Hey you tends to get everybody's attention, so please use whatever you feel comfortable with. So what I'm going to do is I'm going to get you to go around the room. I find it a little harder to get to learn people's names with the masks on, so we'll try. And I think I have, over the courses I'm teaching, I think I have about 70 students, so I might take a while to get to know you. So if we could start back here and work along, and just let me know your name, your major, and let's go with your favourite art school.
My name is Nick. I'm mechanical engineering technology major.
Perfect. Very good.
My name is Jocelyn. I'm mechanical engineering major with aerospace application. And my major is in technology. My name is Anna. I'm studying mechanical engineering. And my favorite topic is computer.
Very good.
My name is Kevin, mechanical engineering. Studies in grade.
My name is Chris.
My name is Chris.
My name is Michael, computer engineering, and my name is Justin, mechanical engineering technology, and
Beata, mechanical engineering, and software vanilla with strawberry.
I'm Donata. I'm a mechanical engineering with a minor in aerospace. And I would say software.
Hi, I'm William. I have a mechatronics robotics major, and my favorite art is coffee. My name is Alex. I'm a manufacturing engineering major, and my favorite color is s'mores.
Good.
My name is Sunny. I'm a mechanical engineering major, and I would say anything peanut butter.
Okay, very good.
My name's Sam, computer engineering, and perception.
Oh, good. Branching out a bit. Yes.
Jason, mechanical engineering, and capture.
Oh, very good.
my name is Mark, computer engineering, technology of the molding.
Okay.
My name is AJ. I'm a mechanical engineering major, and I'm studying software.
My name is Max. Computer engineering, and my favorite art flavor is cookie dough.
Very good.
My name is August. My major is robotics engineering, and I'm also on the pistachio train.
Oh,
So,
cool. Very good.
My name's Jack. I'm a computer engineering major, and my favorite ice cream is coffee Oreo.
My name is Marcus. I'm computer engineering technology, and my favorite is Ben & Jerry's fish food.
I'm William. I'm a robotics major. I'm big vanilla.
Okay. So I'm surprised. Normally I get somebody who says they don't like ice cream, and they give me another dessert. Whether it's I had one person who preferred just mango as a fruit as their dessert. So I forgot to add that if you didn't like ice cream, you could go with your favourite dessert. Okay, so we have a bit of a mix of class. I think I got everybody's. Did I miss anybody from that list? I think I checked. So I don't have a required textbook. You do not need to have the textbook. Most of everything that I'm doing is taken out of this book. So if you need some backup, if you're not getting what you need out of the lectures and talking to me, have a look at the textbook. I also recommend some very good online videos about circuit analysis, places like Khan Academy and that sort of thing. Even just generic YouTube ones. There's a lot of good stuff out there. I will also try Professor David Broderick, who's also in the CET program, has a lot of videos as well, and I'll see if I can get links to his circuit analysis and post them in Blackboard. Okay. So we're just starting today, so there wasn't any real prep. I did ask you to watch that half hour or so video to start with. I'm going to try and basically reproduce that video live shortly, and then we'll see how that goes, just to try and take you through some of the things we're doing. But normally I will post, usually on Saturday or Sunday evening, a list of stuff that I'd like you to do before the next session. And I could be looking at a lab, I could be reading some stuff, I could be watching some videos. I have topic videos for all of this, so you'll see somewhere back here maybe. I have all the videos from previous sections. You'll also notice something odd. I have people's exams. So one thing I do a little differently from a lot of professors is I do my midterm and my final as online oral exams. What I do is I release the exam paper about 2 weeks before you have to take the exam. You then go into that bookings link that I showed you earlier and make a booking for your exam, about 20 minutes. And the exam paper covers everything I think you need to know. However, I can't ask you everything in that 20-minute slot. So I will ask you a subset of the questions. And you need to answer them. And I have found that students tend to be able to show what they know and what they don't know much faster for me as an oral exam than a written exam. You'll get plenty of chance to do the written stuff outside of the exam. There's lots of homework. But what I'm looking for is in the exam is that you understand what you're doing and you can explain. Because I found that if the student can explain what they're doing and why they're doing it, they get a much deeper understanding of the subject material. But anyway, there's several. Let's go to the playlists maybe. I think I have in Blackboard a link to the full playlist for CET236. Again, my lectures from over the summer. do that here. So within Blackboard there's a link on the side here that says Tools for Remote Work. That bookings site is that first one. And I haven't set up this playlist correctly yet, but I will put all the videos that I'm making at the moment in that playlist. I'll also put previously when I've been online, remote, I've been doing my lectures over Discord. I do have a Discord server. Sometimes that's the quickest way to get a question answered. I mean, not unless we go remote, I'm not going to use that. And this is the old version of the link to OneNote. I have to update that as well. Remind myself. Okay. So that is, I'm not going to go through that, that's just got all the chapters in the textbook, and the ones without a cloud on it we're going to cover. The ones with a blue cloud we partially cover, and the ones with a red cloud we don't cover at all. Right, so there's some stuff there. I have there is a syllabus in Blackboard and in OneNote. They should be the same. The key piece here is the grade, right? 30% homework, 20%, midterm is 20% of the final exam. Because a lot of you probably haven't done an oral exam before, think of the midterm as practice. What I'll do is, if your final grade is better than your midterm grade, I'll just replace the midterm grade with your final. Right? So if you bomb out on the midterm, then there's a chance to be better on the final. So homework is due when it's due. I have links in Blackboard, but the actual system that does the homework is a thing called ZBrush that Professor Broderick has set up. So that will take you to a link there. There's no need to actually submit the homework in Blackboard, provided you do it in ZBrush. I copy the grades across. You do need to submit your lab into Blackboard. So that's only homework using WebWork will be accepted. I don't take emailed or physical copies. Similarly with labs, only labs submitted to Blackboard will be accepted, and I don't accept emailed or physical copies of labs. Due dates are final. Once you pass the due date, that's it. You get 0 for that piece of assessment, whether it's a lab or a homework assignment. However, if you tell me before the due date that there's a problem and you need an extension, I'm usually okay to give you an extension before the due date. The other thing is, as you can see there on free passes, I give every student 2 free passes on labs and 2 free passes on coworker side. That means for no reason or any reason, you could ask to resubmit or submit for the first time late any 2 assignments. I suggest you keep those until towards the end of semester. Don't burn them up in the first 2 weeks or the first 3 weeks. That way you can see what the best bang for buck is. And yeah, in case you hadn't noticed, I am partially deaf, so I may ask you to speak up, particularly with the mask sections that make it. I didn't realise how much I lip read until we started wearing masks. Right, so if anybody else has an accessibility issue of any kind, please let the university know and let me know if there's anything I can do to improve that. Please do your own work. Please don't share your work with others unless I ask you to. Perhaps in particular I tend to let people work together. Maybe not physically, but virtually. So please keep it all above board. I want you to learn. I don't want you to learn or to just use other people's learnings. And the rest is just the topics I had before. Okay, any questions so far? Okay. So let me do this. Let me, I haven't practiced this talk for a bit, but let me see if I can start here. That's the topic list we've got to get through. We're going to go through this left-hand column first. And let me just draw. So we're going to go through this left-hand column first with resistive circuits. And then we're going to do the whole thing again, but with some extra bells and whistles. Operational amplifiers, inductors and capacitors. So two of the, there it is. There's 2 pieces of background information that we need to cover. Linear algebra and complex numbers. Everybody okay with complex numbers? Anybody not okay with complex numbers? No? How about linear algebra? What are your matrices and vectors like? No? Okay. So they're the sort of 2 building blocks we need. Linear algebra, in order to do mesh analysis, nodal analysis. And complex numbers, again, we need, once we start looking at capacitors and inductors. Okay, so let me start talking about the stuff we've got to talk about. Right? I use that acronym to start everything off. Right, so we've got, let me see if I can make it a bit smaller, there we go. So V is for voltage, right? the units are volts. The symbol for the unit is capital V, and then I usually write a variable that is a volt, or that is measured in volts, as either capital V or curly V. Right? As I said earlier, we use I for current. The units are amperes. The symbol for the units is capital A, and the variable is either I or script A. P is power. Any guesses what the unit for power is? It's not horsepower. Watts. Very good. So SI units only, right? Not American customary units. And the symbol for watts is W, and I usually use capital P or small script p. E is energy. Guesses on what the unit of energy is? Joules. Very good. Capital J, and again E or script E. R is resistance. That unit is ohms, and now we get a bit funky, and we go with the omega. So it's a capital omega, and it's not to be confused with the Greek letter that's in the papers these days, the omicron. Difference between the omicron and the omega is omicron is little o and omega is big O. Okay. So there's an omega, and I usually use just capital R for the variable. Now Z is a funny one. Z is actually impedance. Its units are also ohms. Symbol is also capital omega, and I use a Z for that. The difference is that for resistance, the value is real valued, and for impedance, the value is complex valued. In case this is the set of real numbers, and this is the set of complex numbers. That's about the only real difference between R and Z. I apologise in advance. Sometimes I revert to my native language, which is Australian English. And that letter at the top of that last column is Z, not Z. Okay, so I apologise if I slip into using Z instead of Z sometimes. Okay, so the other thing we can do is there's some relationships here, right? One of the relationships is just give us a bit of space up the top there. One of the relationships is between V, I, and P. Right? We can put those three together and we get P equals VI. So the power often dissipated in a device is the voltage drop across the device times the current through the device. The other relationship that we have is V equals IR, which is Ohm's law. And Ohm's law is what we use to do a lot of the analysis. We could also throw in Z and say the same thing, but now with complex numbers, V equals IZ. Okay, so this goes again. Okay. So I've talked about voltage, current and resistance. I've talked about power and energy. Let's go with series circuits. So I'm not going to talk about inductors and capacitors, but I think that we can do the same thing with them. Right, so a series circuit, the definition of a series circuit is that two devices uniquely share a common node. Now we've got to decompose that a bit. Two devices uniquely share a common node. So if we're drawing two series resistors, then we get that, right? There's R1 and there's R2. This piece here, and this piece here, the wires, the wire at the end, the wire connecting the two, and the wire at the other end, these are nodes. Oops. And a node is an area of constant voltage. Now it does get a little confusing. I've said area, right? But oftentimes when I refer to a node, I will just draw a dot like that, right? Or let's see it through the right. I'll actually refer to the node by a dot, but what I mean is all of the wires connecting into that dot. So hence I use the word area in the definition. Okay, so there's two resistors in series. And we can rewrite that as a single equivalent resistor. And the value of that single equivalent resistor is just R1 plus R2. Can you prove that? So one thing I'd like to try and do is justify things like this from first principles. And I want you to get used to trying to think through from first principles. What do we know about this circuit? Sorry, no? What? There's two resistors in series? Yeah. What else do we know about the circuit?
There's 3 nodes.
There's 3 nodes, that's good. What do we know about the circuit? I think they're taking it easy. Yeah? Ah, now we're getting somewhere. Right? We've got a voltage and a current. Anybody want to expand on either of those? That's a good start. Any other thoughts about voltage and current? Yeah? They are related to resistance, right? So we could say something like, so we had Ohm's law, right? V equals IR. We can rewrite that to say R equals V on I. Okay? Now, anything else we know about the circuit? So we know, we said it earlier, we've got this. 2 devices uniquely share a common node. Right? And we have I1 flowing here, and we have I2 flowing here. What can you say about the relationship between I1 and I2? Yeah, Mike?
R2 current is affected by R1. R2's current is affected by R1 because of the series.
Very close. There's something even more definite we can say. So,
I2 will always be less than I1?
So what is current? You're on the right track, right? What is, yeah? Electrons flowing through the circuit, right? So we have electrons, or perhaps a better way is charge, right? The reason we say charge rather than electrons is electrons are really, really, really tiny. And you've got to use huge numbers if you do this in terms of electrons. Right, so we have electrons flowing in here. Where do they go once they get into this node?
Into the next resistor.
Into the next one. Right? So what we have is I1 has to equal I2. Right? So we can just say that that's I and that's I. Now, one of the fundamental laws that we need to understand in this course actually captures that idea. Right? And let me just see if I can. So if I have a series of wires with currents I1, I2, I3 and I4 flowing into them, there's a thing called Kershaw's current law, which says that I1 plus I2 plus I3 plus I4 equals 0. That's one way to say it. The sum of the currents flowing into the node is 0. Another way to say the same thing is the sum of the currents flowing into the node must equal the sum of the currents flowing out of the node. Right? And it all depends. This is one way to do it. The other way, the way I just said it the second time, is if we have alright, so there's I1, there's I2, there's I3, and there's I4. Here now we have the sum of the currents flowing into the node, I1 plus I2, equals the sum of the currents flowing out of the node, I3 plus I4. And that second way of saying it is closer to what we were talking about with the series circuit, right? I1 flowing into the node has to equal I2 flowing out of the node. So now let's think about our equivalent resistor. Right? Our equivalent resistor oops, let's just scroll it up a bit so we can read it. Right, so the V total across the single equivalent resistor divided by I is equal to V1 on I plus V2 on I. Or we can just cancel out all the I's and say V total is equal to V1 plus V2. So I hope you can sort of see that if we measured the voltage across V1, or across R1, it would be V1. If we measured the voltage across R2, it's V2. If we measured the voltage from the right-hand side of R2 to the left-hand side of R1, it's V1 plus V2. Okay. Let's just go back to our list of things and see where we are. So I talked about series circuits. I talked about Kershaw's current law. I've talked about Ohm's law. You'll notice I didn't say anything, but you would have noticed that I added some polarities on my V1 and V2 when I drew them. Arguably the most fundamental thing you will learn in this course is a thing called the passive sign convention. So let's talk about that. And then we might have a break, because I've been talking for nearly an hour. So let's have a look at that. And let's make it slightly thicker. Sign convention. These devices, apart from maybe if I've been charging myself up with static electricity, they're not going to give me a voltage drop, right? There's no voltage there. Same with these. Right, again, you may have heard of a thing called a supercapacitor. That's basically one of these things, but with a much higher value for its capacitance than normal. But unless that capacitor is charged, it's not going to give me a zap. These devices are passive. They're not batteries. They're not power supplies. Right? So this idea, the passive sign convention, applies to passive devices. R, L, and C devices. It does not apply to batteries or to power supplies. And the sign convention is simple. If you have a device, and I'm going to draw a generic box because it could be a resistor or a capacitor or an inductor, then so the voltage, the low side is on the right hand side and the high side is on the left hand side here. And the current flows into the positive. Now think about that. I bet you've drawn a circuit with a battery in it and had the current flow out of you always, that's what you get taught in physics, right? When you're talking about current flow, it flows from positive to negative. This is counterintuitive from what we know. And the reason is because, sure, a battery is an active device. It causes current flow. But we're interested in the passive sign convention for passive devices. So we need to have the current flow into the positive and out of the negative. If that is true, then two things hold. Ohm's law works. V equals IR. If I didn't have this happen, if I had the current flowing that way, or if I swapped the positive and the negative, Ohm's law would come out as V equals minus IR, right? Which doesn't really help. You're better off having V equals IR. So that's one reason. The other reason is that if you have the device, a passive device, following the passive sign convention, then P equals VI tells you the power dissipated in the device. Remember, if you had an active device, that active device will generate power. It will provide power. These are passive devices, so they consume or they dissipate power. Again, if my passive device didn't follow the passive sign convention, that equation would again be P equals minus VI. Okay? Because a passive device has to dissipate power, so the negative of dissipation is generating power. Just about everybody will trip up on this, but we're going to practice it enough so you should get used to it by the end of the course. Okay, let's have a quick look at the list. And I'm going to take a quick break and get some more coffee into me. I've been talking for a bit, but we have talked about the passive sign convention as well. And when we come back, I need to talk about parallel circuits, combination circuits, KCL. Any questions so far? No? Okay. Let's. I usually take about a 10-minute break, and we'll come back in about 10 minutes. I'll put a 10-minute timer. OSHA compliant. Yeah, good. Everything sorted out or ready to jump into it?
Yeah.
Yeah, good. Just, let me know if you need it.
Yeah.
one of the problems with getting a new lab is unpacking everything. And that is new stuff. Whatever you do, unless there is an emergency, don't press that red button.
Got it. Do we know what it does?
You know what it does? It cuts power to it. Right? So,
You didn't put a label on it.
I would have thought so.
Or like a cover.
The cover too, yeah.
Like definitely
So
estimating
just
against
be
us.
careful. It's probably okay, but most labs should have one of those, a power cutout, right, just from a safety viewpoint. But I hadn't seen it until just then. So I knew it had to be here, I just didn't know where it was. And most of the stuff in this lab is low voltage anyway, so it's... There we go. Let's stop that. Okay already. Thank you. Okay, let's think about going back to it. Any questions come up while we were having a break? So I can talk for as long as 2 days. But I find I do better if I have a break about every hour. I'm not going to talk at you for 4 hours today, even with breaks. Not going to happen. I want you to do some lab time somehow. We'll have to figure that out. Next week I should have access to the lab next door as well. But part of what I want to do in this is make sure you have access to lab equipment. One of the pieces of lab equipment is a prototyping board, right? And what you do is all of your circuits are going to be put together using one of these boards. Now these boards have lots and lots of holes in them, as you can see. And different sets of holes are connected differently. Right? Different holes are connected together differently. On this board, all of the holes down this red line, see that? All of those holes, they're all connected together electrically. All of the holes down the blue line, on the just beside the red line, the line of red and the line of blue are not connected together electrically. So normally, the red line is for the plus side of the voltage supply, and the blue line is for the minus or the zero side. Same with this one, same with this one, same with this one, same with this one, same with these two. Right? The long lines of red and blue are connected together, but they're not connected to each other or anywhere else. This red one is not connected to this red one. This blue one is not connected to this blue one. Just the adjacent red ones and the adjacent blue ones. All the other holes are connected differently. These five, F, G, H, I, and J, are all connected together, but the next row up are also all connected together in a row, but they're not connected to the row below or the row above. Holes A, B, C, D, and E are all connected together, but not to the ones above, and not to F, G, H, and I. The reason why that is, we're not going to use them in this course, I don't think. For some courses here, we use ICs, and that line there is an electrical break. There's no connectors from one side or the other, so we can push one of those ICs and connect up to the IC, the integrated circuit. Okay? The reason I said ooh is because that device is an inductor, right? And you'll see it looks very similar to an electrolytic capacitor, which I'll put beside it shortly. Right, it looks different sizes obviously, but it looks pretty similar. The difference is this guy has this top here is a very thin piece of aluminium usually. The top here is actually ferrite material. Right? So it's a magnetic material. Because inductors, as I said, are loops. So in order to make a higher inductance in a smaller package, rather than just having a loop of air, they have a loop around the magnetic material, that ferrite. And that's what that grey material there is. We're going to be using, we're not going to be using IC. I'll see if I can find some others we made, but we are going to be using these prototyping boards. And all you do, is you take the resistor and you bend the legs, usually like that, and you can just put it there, and push down, and it's floating a little bit above, so you can put my finger underneath it there. But now there's a electrical connection from this lead into that road, and from this lead into that road. And then I can make other electrical connections. Many of you will do this. Can you see what's wrong with that? It's connected to itself. Exactly. Just be aware that that whole row there is all electrically connected together, so doing that is probably not what you need to do. That is more likely what you need to do. I probably should have put it one row down just to make it a bit prettier. Okay. sorry, a little bit of intermission. Let's talk about parallel circuits, combination circuits, and Kershaw's voltage law. So let's just go back to Kershaw's current law. I almost never call it Kershaw's current law. I nearly always use the shorthand, and funnily enough, Kershaw's voltage law, I never usually use the full name. I usually use KVL. So let's talk about Kershaw's voltage law. And I will write it out. And it's got a very, very similar form to the current law. Except now we're talking about voltages instead of currents. And we're talking about a loop. And what Kershaw's voltage law says is V1 plus V2 plus V3 plus V4 equals 0. And you have to have the passive sign convention apply, so those voltages have to have those polarities. Is the sum of the voltages around a loop is 0. Now, just like we had to define the word node before, remember a node is an area of constant voltage. Now we have to define the word loop. And a loop is a closed path around the circuit that does not cross over itself. Okay, so that loop there that I drew is a loop. It doesn't cross over itself. You could imagine, and it's a closed path. Closed path means it ends where it begins. Okay, so it connects back up to itself. You could imagine having a more complex circuit right? Making sure I've got everything electrically connected maybe. Now there's a few loops here. There's a loop. There's a loop. There's a loop. Right? They're closed paths through the circuit. This one, I probably shouldn't have used red for the right ones, but anyway, this one is not a loop because it crosses back over itself, right? It's a figure eight. The two red small circles, they're loops. The big outside one, that's a loop. But the figure eight one in the middle is not a loop. It is a closed path through the circuit, but it crosses over itself. Now, there's another term that I'm going to introduce now that we're not going to use for a little bit, and that is a mesh. You may have seen the word mesh analysis, right? So I'm going to talk about mesh analysis shortly, but I thought I'd introduce mesh now that we're talking about loops. A mesh is a type of loop. Oops, not mine. There we go. So a mesh is a loop that cuts no branches. What's a branch? A branch is a circuit component. It's not a wire. It's a resistor, a capacitor, a power supply. Right? So now this loop here is a mesh. This loop here is also a mesh. Let's go with that one. This loop here is not a mesh because it cuts through this device here, right? That branch. Okay. We'll talk a little bit more about meshes over the next couple of weeks. Node, loop, mesh, branch. They're the four main things we use to talk about pieces of a circuit, or the geometry of a circuit. So we talked about series circuits. The other sort of circuit that we could have is a parallel circuit. And again, what we're interested in doing is converting, like we did with the series circuit. We want to convert two devices in series to a single equivalent. Now we want to convert two devices in parallel to a single equivalent. Oops. And two devices are in parallel if they're connected between the same two nodes. Okay, so here is a node. Remember, a node is an area of constant voltage. And here is a node. Again, it's an area of constant voltage. And those two devices, R1 and R2, are connected between the same two nodes. Now remember what we did with the series devices. With the series devices, we figured out that R1 had the same current flowing through it as R2. What's the same here? Now I haven't prepared correctly for this course because one of the things I do in my spare time is I write apps, and I have a little app that I can download all of your pictures from Banner, and I can randomly choose people from the list. And I forgot to update it for today's class. I'll have to remember to do that. And I'll try, with that app, I can keep track of who I picked on and who I haven't. So I will try and remember to put that answer next week. Otherwise, I tend to get the same people answering questions, whereas I like to have everybody at those questions. So what's the same about R1 and R2 now that we're in parallel? Right? The voltage, exactly. They're connected between the same two nodes. Nodes are areas of constant voltage. So here we've got V1 equals V2. Right? So it's just V. So here we've got V equals I Req. And here we've got V equals I1 R1 and V equals I2 R2. Right, and they're all equal. The difference, though, is this, right, I. Right, this is our, I'm going to call it IEQ. The difference is that IEQ is I1 plus I2. You can think about it like this. If you've got IEQ flowing out of here, you've got I1 flowing in, you've got I2 flowing in. So remember Kershaw's current law, the sum of the currents flowing into the node equals the sum of the currents flowing out of the node. Right, so then we've got V equals I1 plus I2 Req. Now the question is, what is the relationship between Req and R1 and R2? That's one way to write it. another way to write it is just or another way to write it is the same here. I suggest you try to avoid remembering this one. It works fine, it is true. The reason I suggest you avoid it is because I will sometimes give you circuits like this. Where we've got more than two. And if we want to find the equivalent there, that form, that yellow highlighted form of the equation is really complicated. Whereas the inverse one is basically the same. Right? Or 1 on REQ is 1 on A1 plus 1 on R2 plus 1 on R3 plus 1 on R4. Whereas that form of this equation, you can imagine it's R1, R2, R3, R4 in the numerator, and then in the denominator it's R2, R3, R4 plus R1, R3, R4 plus R1, R2, R4 plus R1, R2, R3, which is just ludicrously complicated. It's much simpler to just remember that one. Okay, let's go back to our list. So we've talked about parallel circuits, we've talked about Kershaw's voltage law. So I'm going to go with combination circuits and voltage dividers and current dividers next. So combination circuits. I will often give you circuits that look like this and ask you to find the equivalent resistance. And now the trick is to apply those two other ideas, parallel circuits and series circuits, alternately, to simplify the 5 resistor circuit into a 1 resistor circuit. Right, so the first thing we could do is something with those. What could we do with those two?
Parallel circuit to make it into 1 resistor.
Right, so we can convert those two into a single equivalent resistor. I'm just going to call it R45. and it's equal to 1 on R4 plus 1 on R5. Right, and the reason we could do that is because there's an area of constant voltage, and there's an area of constant voltage, and R4 and R5 are connected between the same two nodes, the same two areas of constant voltage. This is also a node, but it's not the same node, so R2 is not in parallel with R4 and R5. Sometimes mechanical engineers think geometrically in parallel is the same as electrically in parallel. They're not. The other thing is, just because they're not geometrically in parallel doesn't mean they aren't, that's not too many knots, electrically in parallel. For example, I could draw something like this, right? Those two are obviously both electrically and geometrically in parallel, but then I could draw this, and it's obviously not geometrically in parallel, but it's certainly electrically in parallel. Okay, so now we have that, and we've got our R1, R2, R3, and R4, 5. Now, I'll go back with the yellow colour. Right, now we've got those two, and they're in series, exactly. So now we can, let's move that over there. Now we can put R1 and R2, and now I'm going to call this one R345, okay, and R345 is equal to R3 plus R45, right, because they're in series. Here's R3, they uniquely share a common node, right, there's our common node, nothing else is coming into that node, so they're uniquely sharing it, so we can just add the resistances. Then let's go back to yellow colour. Now we can do something with these two. What's the relationship between R2 and R345? They're in parallel. Again, they're not geometrically in parallel, but there's a node, and there's a node, so they are connected between the same two nodes, so they're in parallel. So then we can say there's R1 and there's R2345, and that's going to be 1 on R2 plus 1 on R345. And now we've got two resistors that share a common node, right? So that means we can write our equivalent as R1 plus R2, 3, 4, 5. And that's what I mean by combinations of series and parallel. Right, you've got a alternate between finding parallel and finding series devices, and then seeing what the redrawn circuit shows you as far as series and parallel. Right, there we go. So let's go with combination, and we need to talk about voltage dividers and current dividers. So voltage dividers and current dividers are basically related to series and parallel circuits. It's just you're looking at the series circuit slightly differently, and you're looking at the parallel circuit slightly differently. Right, here is a series circuit. But now, instead of thinking about the equivalent resistance, we're now looking at the voltages. We've got a V in on one side, and we've got a V out on the other. Right, so what's that? So we've got our current in. Right, so V in equals I in times R1 plus R2, because R1 and R2 are in series. No other current flowing, we haven't connected anything up to these terminals. So we've just got I in. So V out is just I in times R2. And if you've done any sort of the relationship between the output and the input, V out equals something times V in, and that something we can just gain from this, right? We can rewrite this equation as I in equals V in on R1 plus R2, and we can substitute that value for I in into here, and we just get right, so we get R2 divided by R1 plus R2 times V. So that's our question mark is R2 divided by R1 plus R2. And that idea is called the voltage divider. And it's basically applying series circuits slightly differently. The current divider is applying parallel circuits slightly differently. I'm also going to call I2 I out. Right, so we have R1 and R2. Now, because the parallel equivalent resistance relationship is that 1 on R equivalent equals 1 on R1 plus 1 on R2, this input-output relation looks counterintuitive, because what it says is the current in R2 is proportional to the resistance in the other branch, right? So in this case, that's saying that R1 divided by R1 plus R2 times R. Right? Even though we're looking at the current through R2, the numerator here is R1, whereas with the voltage divider it was a little bit more obvious. The numerator was R2, the resistor that we were measuring the voltage across. Voltage dividers, current dividers. These devices, these resistors, are physical devices. You have to manufacture them. They're made of material. So part of this course, a small part, but I think it's an important part, is we need to understand the relationship between this physical device and the electrical quantities we're measuring. And there's two pieces to that. One of them is, given a material, and most of these resistors we use are carbon resistors. Some of them are tungsten, which is a different. I suspect those blue ones are they're called metal films, and I suspect they're part of tungsten. But these brown ones are more than likely carbon. The fact that it's carbon means that there's some quantity in there of the material, of carbon, that says how big the piece of carbon is in order to give us a 270 ohm resistor. Right? And that's the resistance from resistivity and shape. The material property that determines that resistance, one of them is the resistivity of the material, carbon or tungsten. And there's a really quite simple equation. Let's just maybe go up here. There's a really quite simple equation that says the resistance is equal to rho L on A. And rho is the resistivity. One of the things I look for in an oral exam is that you use the words we use in the class correctly. So be careful with the difference between resistance and resistivity. Right? Resistance is measured in ohms and is a quantity of a resistor, a thing you can measure about resistance. Other things too, but resistivity is measured in ohm meters and is a material property. If I change the material, I change the resistivity. So I find when I learn a new area, a new subject area, understanding the variables, the VIR, understanding the... Oops, something happened. Understanding the material. Okay. So, like I said, resistivity is in ohm meters. Well, that's the other thing. The acronyms. I don't use too many acronyms in this course, but if you're understanding a new area, learning what the acronyms mean is a good thing. So, like I said, understand the difference between resistance and resistivity. The other two things here, L is the length of the object. Oh, I'm sorry. I usually bring in a plastic dinosaur because, and I forgot to bring in it is actually an Apatosaurus, but I'll try and draw it. And A is the cross-sectional area. Oops. I knew I forgot something this way. Right, so if we have a cylinder, right, there's the cross-sectional area. There's the length and the material that it's made out of gives us the resistivity. And combining those three, the resistance. Now the reason I talk about an Apatosaurus or something silly like that is because it lets you, if you know what the material is, you can look up its resistivity, and using just this simple equation you can sort of say, okay, right, and I'm terrible at drawing, so forgive me. If you have something like an Apatosaurus, right, it's one of these big dinosaurs that has a long tail and a sort of cylindrical body and a long neck, right? What you can do is you can say, well, okay, let's approximate this Apatosaurus with a long neck, a barrel body, and a long tail. And let's just assume it's all cylindrical, right? And then I can find R1 equals rho 1 L1 on A1, R2 equals rho 2 L2 on A2, and R3 equals rho 3 L3 on A3. Now if I want to measure the resistance of my Apatosaurus from the tip of his nose to the tip of his tail, what's the resistance? In series, exactly. Right? So our Apatosaurus equals R1 plus R2 plus R3, because they're just in series. And it's only an approximation, right? If you want to do it really, really accurately, you'd do like a finite element analysis, right? You'd cut the apatosaurus up into very, very thin cylinders and then integrate over the cylinders, right? But sometimes as engineers we do that, but I like also being able to get a quick and maybe not so accurate, but okay accuracy answer by just splitting it up, doing something like this. Right? We need to do both, but getting a handle quickly, I think, is sometimes better than never getting the. So that's one thing about the physical properties of these things. The other one is if I put this its resistance would change. If I put it into a freezer, its resistance would change. One of the biggest problems with electric vehicles is to do with their battery. But it's not what you think. There is the range problem, right? It's only now that they're starting to get decent range out of the battery. But in this climate, years ago, the only sort of battery you could use was a lead acid battery. And having that amount of fluid around in this climate could be problematic. Right? So we need to talk about how temperature affects and it's really, again, it's another property of the material, like carbon resistor. So my resistance at a given temperature T is my nominal resistance times 1 plus alpha times the difference between the current temperature T and the nominal temperature. And this alpha is a material property. So if I have my carbon resistor and I heat it up higher than the nominal, what happens to its resistance? Sorry?
It goes down.
It goes down. Why does it go down?
Well, I think it'll expand due to heat and as the process
You're right, it will go down. But it depends on the sign of alpha, right? For a carbon, alpha is negative, right? So if the temperature goes up, the resistance goes down. Different materials have different alpha coefficients. Some materials have a positive alpha. So if the temperature goes up, the resistance goes up. So you can think of space-rated electronics. Right? There's a huge variation in the temperature that spacecraft have to deal with. So carbon is not a great thing to make space-rated resistors out of. They tend to use an alloy that mixes negative alpha material with positive alpha material, so the alloy has an alpha close to 0. Right? So they don't change resistance much as the temperature does. It's hard to get exactly 0. Okay. I'm about to have another break, but let me just quickly check off. So when we come back, I'm going to talk about some of the algorithms. I am going through in today's session everything you need to know for the whole course. Do not be scared if you don't understand everything I've said so far. We're going to go back over it in a little bit more detail. Right? What I thought I'd show you, if I can figure out where it got to. There it is. Let's see if I can find the most recent one I took. I think it's summer. There we go. So here is the summer sessions midterm. And this has, I think, 4 or 5 topics. One topic is charge, one topic is resistivity, resistance versus temperature, and then we get on to mesh analysis. And I don't think I had nodal analysis here, but I may have. Let me just check. I did have nodal analysis. So here's a table of, in the middle column, the rho values, the resistivity values, and in the right-hand column, the alpha values, the temperature coefficients. And you can see for the metals, those alpha values are positive. And you can think that, you know, if you heat up a metal, things are going to bounce around a little more, so the resistance is going to go up. Whereas things like carbon or graphite, down the bottom, quartz, I include hard rubber so we can talk about my Apatosaurus toy. The alpha values are negative. Okay. So it depends on the So let's just have a quick look. I haven't actually talked about these. I'm going to do this maybe after the break. What is the current through a conductor of X electrons pass through a cross-section in Y time. And it's basically relating electrons of charge to coulombs of charge to amperes of current. And then here's resistivity, cross-sectional area, length, material, times resistance, or turn those around and what's the resistivity, or how long is the option. R equals rho L on A in some form or another. And there's some resistance versus temperature. Notice the temperature is in degrees Celsius. I don't like what I call trick questions. Right? If I tell you the temperature in Fahrenheit instead of degrees Celsius, I will put a note like this. Right? Anybody know the conversion from Fahrenheit to Celsius or the other way? Anybody got the numbers? Where are they equal? Where are the degrees Celsius equal to the degrees Fahrenheit? Minus 40. Minus 40 Celsius is the same temperature as minus 40 Fahrenheit. 0 degrees Celsius is 32 Fahrenheit, and 100 degrees Celsius is 212 Fahrenheit. One combination, one pair of those three pieces of information, the equality point, the freezing point of water, or the boiling point of water, should give you let you figure it out. It's basically C equals 5/9 times open parenthesis F minus 32. Now you've got to subtract that 32 and then scale by 5/9. Okay. Let's take that break, another 10-minute break, and then I'll quickly go through mesh, nodal, superposition, Thevenin, Norton, and maximum power. In no way will it be in depth at all, just to give you a flavour, and then we'll go back and get into some more detail probably next week. Okay, so let's do that break. Any questions? Sorry. Real good? Yep, okay. It depends on how you write it. Right, so some people write rho like that. Yeah, I tend to write it like that. Okay, but it's no. I apologize. Yeah, it's a Greek letter rho is what I'm trying to write. Okay.